Hey folks, so here we are going to start looking at centroids of volumes. Now, to go back to what we did when we did centroids of areas, that what we've been working on, if we had kind of like an area here, we started out by taking a little area dA, but then we would have to integrate left to right and up and down. Yes, we'd have to do a double integration, and no one wants that. So what we did was we changed our little elemental area to a strip that was the height of the object, and then we only had to integrate once, yeah, left to right. So when we have a volume like we see here with a cylinder, we do the same thing, use a strip, right? But then we're going to have to integrate still in two directions. So like our volume here, or let's say the volume of our element, we've done this kind of little column shaped matchstick looking element that we call dV, and that's going to be Z, which is the full height of the cylinder. So that's not going to change, and we're going to integrate in X and in Y. So we still have two integrations there. And that may be necessary, it may not. We can sometimes simplify it further by taking a full-on kind of 3D shaped disk and do something like this. So now we're in a situation where, provided we have an expression that relates the radius r with the position x, in this case we take a circular disk as our element, and then we're only integrating in this one direction. So we reduce that to a single integration again, which is what our goal hopefully is. So the centroid of that, we've just basically got a disk with an area pi r squared and a thickness dx. So the volume of that little element is going to be the area times the thickness, so pi r squared times dx, and we're only integrating in x, and that's how we would do that. So to find the centroid of this, obviously in the y and z directions, the centroid are going to lie on that x-axis, right? So where y equals 0 and z equals 0. So we're looking to find the x centroid of this one. So our x centroid is just going to be kind of the same thing as what we've done before. The x centroid of our element multiplied by our elemental volume, the volume of that element, our little dV. And then on the bottom, we're going to add all those volumes up to get the total volume. So it's really just the same as what we did with areas, except when we had dA, we now have dV, and we're finding the volume instead of the area. So in terms of actually doing these, we're not actually going to go through any examples or do any of these centroids of volumes by integration, but what you'll see in the other video that I've put in a link for is that we're going to actually look at doing those centroids of volumes that are made up of composite shapes, because we know that, for example, the centroid of some kind of cuboid type shape, well, we know for a rectangle, right, if there are lines of symmetry, if we have two lines of symmetry, the intersection of those two lines of symmetry gives us our centroid, right, for a two-dimensional shape. Now, if we come in and we say, now we're talking about planes of symmetry, right? So we cut a plane through the center here. Yeah, we've just basically cut a slice straight through the middle. And then we can also cut a plane here. And where those planes meet actually makes a line, yeah? So everyone see that? So we've got these two planes that kind of meet each other along this line here where they intersect. But we also have a plane of symmetry this way. So that plane of symmetry is going to just cut through this line right in the center. Those are going to meet. So now, as I say, we've added an additional plane, and it's going to kind of cut right through there, if we were to imagine what that would look like. I know my drawings are not very good. Hopefully you can kind of picture what I'm saying, but essentially now we're talking about planes of symmetry, and if we have three planes of symmetry, because we're working in 3 dimensions, if we have a point of intersection between 3 planes of symmetry, that's where our centroid is, yeah? So for like a kind of rectangular prism cuboid type of a thing, we know it's going to be smack dead center. Oh, excuse me. And we're not there yet. It's going to be smack dead center. Same thing if we have like a sphere, it'll be in the center of the sphere. Now, as with the centroids of areas, you do have a table in your textbook. So it's either inside the front cover or the back cover. I think just inside the back cover you may find something, or also in the chapter, the section that deals with this, you should find that. So go take a look at that other video that I've popped in the link under the assignment, It's going to go through and show you how to do this method of finding centroids by volume, centroids by composite shapes of composite volumes, and doing that using a table exactly the same ways we did with the areas.